Hello, welcome to what hopefully will be the first in a long series of some online videos that will hopefully go through the remaining of the material that we have for this semester. I'd like to start our first video by talking about the solutions to our last test, and also in the course of doing that, just have some basic review of some of the circuit analysis techniques and issues that I think we still need to resolve from material that we've started since the beginning of the semester. I'd like to start off by talking about the most basic of the laws that we learned in the beginning of the semester, Kirchhoff's voltage and current laws. So at face value, it seems like this is relatively basic. The sum of the voltages around a closed loop is 0. The sum of the currents into and out of nodes are 0. However, there's some details in the way that we apply these rules, which I think still deserve some practice and comment. And so I'd like to go over those now in the context of the problem that we had on our third exam, which is now shown up here on the screen. So let's start by first picking one node to which to start our summation. And to make sure that we include all the terms in the summation, I personally think it's a good idea to just kind of put a little red dot where we started so that we can make sure that we actually end there when we're done writing our equation. The second thing to note is that all of the voltages around a loop need to be summed in the same relative direction. So for example, suppose I had any set of elements. It doesn't even necessarily have to be voltage sources or resistors, just any element which is forming a loop. I have to make sure that I sum all of the voltages around the loop in the same relative direction. So if I have one being minus to plus, the next one should also be minus plus, minus plus, minus plus. And if these are the relative directions, then we can write this such that all of the voltages have a positive sign and we just add the voltages together. So when I'm adding around this loop, I'm going to have to decide one sign based on the relative direction of the voltages. And then the next sign I'm going to have to design based on the sign convention of Ohm's law. So let's start and look at the 6 volts. Because I'm having a minus to plus transition, I'm going to write that as a positive 6. Now I come to the next element, which is a 1 kilo ohm resistor that has a current Ix through it. And here is where Ohm's law comes into play. So remember what the positive sign convention for Ohm's law was. If I have a resistor R, which has some voltage V across it, then I have a positive sign when I'm writing Ohm's law if the current is entering the positive terminal. So, given that my Ix has already been labeled for me, the positive direction of the voltage across the 1 kilo ohm resistor is how I've just indicated it now with the plus and minus signs. But notice that the relative direction of this voltage is opposite the direction of the 6 volt. In other words, when I'm going along the path, when I'm going over the 6 volt source, I have a minus to plus transition, whereas now I have a plus to minus transition. This means that I have to write the voltage with a minus sign, indicating that I have a difference in polarity on the voltage. And then I have to write Ohm's law. And in this case, I've indicated the voltage so that I'm using the positive sign rule for Ohm's law. So I don't have to add another negative sign. With Ohm's law, it's just going to be 1 kilo ohm times the current, which is Ix. Applying the same logic to the next resistor, I can write similarly that this is going to be minus 2k times Ix. This now brings us to the point right above, the node right above the 2 milliamp source. And in order to kind of proceed, I now have to go across 2 successive 12 kilo ohm resistors. The first thing that I'd like you to notice about this triangular shaped topology is that due to the short circuit connection that I'm highlighting here above, actually the 12 kilo ohm resistors are in parallel. Notice how they share the top node and they also share nodes on the other end. So what has been labeled Vx across the right 12 ohm resistor can also be said for the same thing across the left 12 k ohm resistor, as so. So there's 2 ways that we can now proceed to go about writing Kirchhoff's voltage law. Either you can say, hey, there's a short circuit connection here. So if I just directly go across that short circuit connection, I can bypass both of those 2 resistors and just say a +0 when I'm going around the loop. Or if you want to be a little more meticulous on notation, with regards to following the purple path, then you can write plus Vx minus Vx. And of course, this sum is going to equal 0, which is what we would expect due to the short circuit connection. Okay, so now we're just to the left of the 8-volt supply. And our next step is to go over the 1 k ohm resistor, but we don't know yet the current that goes through the 1 k ohm resistor. Now, there's a couple of ways that we can calculate this current. One is by applying KCL at the top node here. The other is by applying KCL at the bottom node here. So let's do them both ways. If I wanted to write this current, let's give it a new name. Let's call this IZ so that it's different. If I want to write IZ using KCL at the top node, you must remember that you can't just add the 12 k ohm current and the current that's through the 8-volt supply. You also have to add this current that comes through the short circuit connection. And that in turn is supplied by these other 3 branches. So another way of thinking about this is the same logic that we used to have with supernodes. If I draw a block around the entire kind of supernode type of connection, then I have to add the currents on all of the branches that intersect with the box. So in the case of IZ, this means that I would have to write that IZ equals IY. And then notice that the current through each of the 12 k ohm resistors here, since they're a reverse sign, they will essentially cancel out, so I don't have to worry about them. But I do need to take into account the 2 milliamp source, which since I'm writing it, let's write it as let's write everything summed outwards, shall we? Then it's going to be IZ plus IY plus 2 milliamps minus IX is equal to 0. Okay, so then you could just take all of the other terms on the other side and you would find IZ, and then you would be able to write it. Now, the other way of finding IZ is in terms of the currents in the bottom node, which in that case, you would find that IZ is going to be the sum of I naught plus Vy divided by 2K. Both answers are acceptable. For shortness, I'm just going to use the bottom method. I'm going to continue underneath by writing minus 1 k ohm times I naught plus Vy over 2K. The next resistor is this 2 k ohm resistor here, which has a current of I naught over it. So this is minus 2K I naught. And now I come over here. Now notice once I get to this node here, there is a short circuit connection that takes me all the way back here. And to close the loop, I now have to find the voltage over the 6 k ohm supply. So this is going to be minus 6K times whatever the current through it. Let's just call this IB for now. And then that equals to 0 because I've closed the loop. Now the question is, what is IB? Now, one way of answering this question is by, again, considering the kind of supernode situation and to draw a box around the entire node and then sum the currents that are going into all of the branches in the node. So if I make a box like this, now note I have to go around everywhere. Here's my box. I have to add IX minus 2 milliamps. I have to add twice Vx divided by 12K because it's being supplied, both of the current from these resistors is being supplied through the 24 volt supply. And then I have Vy divided by 2K plus IO and IY. The thing that you must be careful of is that you also have to add the current here, which, because it shares the branch with the 6 k ohm resistor, is also IB. And so you get a situation where IB equals a lot of terms minus IB, or yes, because we're summing outwards, minus IB. And so that makes it kind of hard to find now IB, because you get a plus IB and a minus IB now in the equation and they cancel out. And so you might say, hey, well, what's going on? How am I going to find the current coming through here? Now, the key thing to observe is that IB is essentially a ground current. It's going from ground, which is here, to, because of the short circuit connection, this is also ground. Okay, and so the easiest way of kind of dealing with this situation is simply to make the observation that the sum of the 6 volts and this term, whatever that current might be, you just make the note that 6 plus, I'm sorry, 6, yep, 6 minus this 6K times IB must equal 0 because of the short circuit. Okay, and then that will save you from having to now independently sum up a cajillion terms to try to find what the current is. Okay, so this problem was really an exercise in recognizing short circuits and being able to take advantage of the ease that that provides. A lot of people in class went through the trouble of trying to write the equation for this very large supernode on the bottom, but it was quite unnecessary. You could have simply said plus 0 and then nixed out those two terms in the equation and you would have been done. So essentially the voltages for the only elements for which we need to sum the voltage are the 1K, the 2K, the 1K here on the right hand side, the 2K here on the right hand side, and we're done. So it was really just a sum of four elements and their currents to be able to do the problem. Okay, so this is again a case where you have to make observations, I think, to make the problem easier for yourself than what it otherwise would have been. Okay, next I want to talk a little more about current dividers. So I think current dividers is an important topic because they come up quite often, and therefore it's important to be able to recognize them. In general, what do I mean with current dividers and voltage dividers? So I want to emphasize that in the case of voltage divider, we have a series of resistors. Okay, it doesn't matter how many resistors there are. They're just strung like beads along a string that connects two nodes. And so what's important here is to first identify the series connection. In order to be able to have a series connection, you cannot have any current being drawn from in between the resistors. There might be a branch there, but then you have to make sure that there's 0 current so that these resistors are truly in series with each other. So we have a series connection of resistors across which there is some voltage, and this could be a node voltage, it could be connected to a voltage source, it doesn't really matter. I'm just going to call it Vx right now. Okay, and so you need to identify the series connection and the nodes between which those resistors lie, and then ask yourself, what is the voltage now spanning that series connection of all of those resistors? Once you do that, then the voltage across any one resistor, let's call this V1, let's call this R1, R2, R3, okay? V1 then is just going to be the resistor that you're looking for the voltage across, divided by the sum of all of the resistances along the series path, times the voltage that spans that series path, okay? When we're dealing with current dividers, again, we have some source of current, IS. It may be a source, it may be another branch, but the key thing is that this current comes and it's then divided between two resistors. Now here, it's important to also consider the signs. It's like fluid flow. So if the source current is coming in this direction, then to maintain consistency, the positive direction of the current needs to be pointing downwards, like it's tumbling over a waterfall. If this is again R1 and R2, and let's call this I1 and I2, then you would find what the current divider is by taking the total resistance on the opposing branch, which in this case is R2, dividing it by the total resistance across all branches, in this case R1 plus R2, and then multiplying by IS. And so this would give you, for example, the value of the current I1. Again, it's important to consider relative directions. If I would have defined a current I3, which was in this reverse direction, then I would have to write I3 as minus R1 divided by R1 plus R2 times IS. And if you look at the case of the voltage divider here, going back again, suppose I defined a voltage that was in the reverse direction, like this V2. Why is it in the reverse direction? Because the negative sign of the voltage is not aligned with the negative sign of the total voltage. It's the positive sign of V2 that's aligned with the negative direction of Vx. So that generates a negative sign, and then you would write this then with a minus sign. So this would turn into, let me write it up here, it would be V2 equals minus R3 divided by the sum of the resistances times Vx. Okay. So now let's see how we can apply these principles to an example problem. So this was the example that we had on our test. And the first question asks us to find using current dividers to find VAB. So the first thing that we need to do is to kind of think about how we would originally find VA and VB. Remember how the notation is defined. VAB is defined as the node voltage VA minus the node voltage VB. Let's define here this point as being ground. I'm going to define the other node as having a voltage Vx so that I'm labeling my node voltages. And now the first question is to find actually how much current we have coming through these branches. We have a divider situation because the 8 amps here comes up and then it splits off into 2 directions. So let's call this I1 and let's call this other current here, the branch current over the 20 ohms, I2. So how would we now write the dividers? Let's first find I1. I1, well, first we have to find the sum of the branch currents that I1 is going through. Now remember that the resistances have to be the sum of all the resistances over the branch, and the branch is defined by the nodes. So where is the endpoints that we need to look at? We need to look at the total resistance between the ground pin and Vx. This A doesn't really matter to us, node A. This is just like a probe. You know, imagine like using a voltmeter or something to measure what the voltage was at that point. There's no current being drawn out of node A or out of node B. So the 10 ohms and the 50 ohms are in series. I could write 10 divided by 50. And the 20 plus the 40 are also in series. Remember, if I'm finding I1, I need to find the sum of the resistances in the opposing branch. So I need to take 20 plus 40 divided by 20 plus 40 plus the sum of the resistance in the opposing branch. And again, you also have to make sure that these 2 branches are in parallel. So we have one connection this way between Vx and ground, and the other connection is this direction here between Vx and ground. So this is going to be 10 plus 50 times 8. And this just turns into 60 over 120, which is 1/2 of 8, and you find that I1 is equal to 4 amps. If you subtract that from 8 amps, then you can find that I2 is also equal to 4 amps. Now, how can we use this to find VAB? Well, VA is going to be equal to 50 times I1, and VB is going to be equal to 40 times IB. Okay, and so if you just go through and kind of calculate this and find the difference, I'm sorry, did I say IB? This should be I2, sorry, 40 times I2. And if you now subtract the 2, since I1 and I2 is equal, you'll find that VAB is just going to be 10 times whatever the current was. In this case, the current is 4 amps. So VAB is just going to be equals to 40 volts. Okay. Now, how do we find the voltage across this 50 ohm resistor using dividers? Again, you have to recognize the series combinations. So the question that you must ask yourself is, what resistor is in series with the 50 ohm resistor? In this case, it's going to be the 10 ohm resistor. Then the second question is, what are the nodes that are at the endpoints of the series combination? Answer, one node is Vx, the other node is ground. So the voltage that's being divided is voltage Vx. Let's assume for the moment that we know voltage Vx and write the divider equation. If I wanted to define, let's call this V50 for V50 ohm. So V50 is going to be 50 divided by 10 plus 50 times Vx. How do I find Vx? I can find Vx by computing the R equivalent of all of those 4 resistors combined together. So let's look at it. I have 2 parallel connections. On each parallel connection, there's 60 ohms. 60 ohms in parallel with 60 ohms is going to be equal to 30 ohms. And that tells me then that this is going to turn into 5 divided by 6 times Vx. Vx is going to be 8 times 30 ohms. And if you go through and you calculate what this will actually give you, you should find that V50 becomes 200 volts when you go through and do the math. Okay. Now I want to talk a little bit about superposition. Superposition is a method where we can independently find the contributions of each voltage source and then later on sum them. The important thing to remember here is that you never close dependent sources. Never. There is not one single technique in which we ever would touch a dependent source. You never close dependent sources. The independent sources are like the pillars, the load-bearing pillars of your building. Your answer, so if our goal was to find Vx, without doing any calculations, I can tell you that Vx is going to be some number times 12 volts plus some number times 2 milliamps. The question is, how can we independently calculate what these coefficients are? The way that we would do that mathematically is by zeroing out one of the sources so that we're only left with Vx contribution of 12 volt supply divided by alpha, for example. But superposition method enables us to do this on the circuit. So if we want to find, for example, alpha, then I don't want to have the 2 milliamp contribution. So I'm going to turn off the 2 milliamp source. And if I want to find beta, I don't want the 12 volt source. I'm going to turn it off and then calculate what's left. And then at the end, I'm going to add the two components together. So now the key thing is, what do the subcircuits look like? Let's go through and actually draw this. Remember, the important point is if I'm looking at the 12 volt source, I have to turn off the 2 milliamp source. So this means taking this 2 milliamps and turning it into a current value of 0. Current of 0 implies an open circuit, which means that this is out. You can think of this as being completely disconnected and there's no current coming through here. Other than that, you don't touch the circuit at all. And if you look at the component due to the 2 milliamp source, then we have to turn off this source. The 12 volts is now going to become 0. A voltage equivalent to 0 just turns this into a short circuit. So it's like we have a wire here. And again, we don't touch anything else. We're just left with these two subcircuits. And once we get these two subcircuits, we can calculate with whatever method we want. We can calculate, let's say if we want Vx, we can calculate Vx1 from here. We can calculate Vx2 from here, again, using any method. And then what do? You take these and you sum them to find your overall Vx. Okay, so that's the main idea behind using superposition. Let's talk about source transformation a little bit. Source transformation is kind of like our introductory step into thinking about Thevenin equivalent circuits. Okay, and so the idea behind source transformation, though, is that it's a little bit more specific than Thevenin. I'm specifically looking at the relationship between a series combination of a voltage source and a resistor. And I'm saying that this is going to be equal to having a current source in parallel with the same valued resistor. So the important thing here is that we preserve the nodes. So if I'm looking at a series combination of source and resistor across nodes AB, then I need to be replacing it with a transformation that's also across nodes AB. And the only other thing that we have to worry about is we have to make sure that our current source IS is equal to VS divided by RS. And as long as this relation holds, then we can transform between the sources. And we can do this even when there is a dependent source around. That doesn't change anything. Again, the key thing is just to make sure that you're replacing your transformation back in the same place of the circuit, which is still across the same two nodes. Again, let's look at an example. In this example, there's two source transformations that can be done. The first is the series combination of the 18 volts and the 6 ohms. The first thing that you need to do is identify that they're a series combination, and then identify the nodes which spans that series combination. So in that case, it's going to be this node here. Let me label it X. And this node here, which has already been labeled B. And now they're going to be in parallel. So I can write over here X and B, and they will now be in parallel. So here's my parallel combination. The 6 ohms stays the same. And then I now have my source, which comes here. And it's V divided by R, so 18 divided by 6 gives us 3 amps. Here's our source transformation, we're done. And now we can continue drawing the circuit across the same nodes. There's also a 3 ohms resistor here, so I need to kind of extend these two nodes out this way to be able to take into account the 3 ohms. But notice there's another transformation that I can do, this transformation here with the dependent source. But we must be careful about between what nodes we're doing the transformation. This is between nodes X and A. So let's draw node A all the way over here. This parallel combination is now going to be in series. So I need to draw a series combination between nodes X and A. So here's my volt source, and here's my diamond shape for my dependent source. Remember that the current source is going to become a voltage source. Mistakenly, some people, after doing the transformation, unfortunately put an arrow through here, implying that this was a current source. This needs to go to a voltage source. What's the direction of the voltage source? The positive sign is going to be aligned with the direction that the arrow is pointing. Therefore, the plus minus need to be aligned, as I've indicated here on the slide. And I'll find what that value is by taking 2 ohms and multiplying it with 0.25 V out, which gives us 0.5 V out. And then the value of the resistor stays the same, so it's just 2 ohms over here. So actually, I can also bring this out here just to make it similar to the original circuit, and you're done. Okay, so again, the key thing is just to make sure that you're aware of what 2 nodes you're transforming between, and make sure that your transformation gets replaced in the across the exact same 2 nodes, so that we're preserving the accuracy of the circuit. Let's now talk about this a little bit more broadly in the context of equivalent circuits. The idea of equivalent circuits is that I can take any combination of linear circuit elements. So I have a linear circuit. It could be dependent sources, independent sources, resistors, anything, as long as the circuit is linear. And I'm again looking across 2 specific nodes, AB. And what I want to do is I want to replace that with a circuit that's just going to be a voltage source in series with a resistor. The idea behind why we can make this kind of a transformation is if you consider going into the lab and just measuring what the VI characteristics of this circuit would be, because it's a linear circuit, this relationship necessarily must be a line. And essentially, the Thevenin resistance and the Thevenin voltage correspond to specific things on this measurement of the voltage current relationship. More specifically, the slope of the line corresponds to R Thevenin, and the intercept here, where the current is 0, corresponds to the open circuit voltage. This is the voltage that you would measure when there's no current. Where is current I? Current I is the direction coming out like so. Okay, so it's the current that's going from the circuit into node A. And we also have a special label for what we have here, which is our short circuit current. This is the current that you measure when the voltage is equal to 0. Okay, so what we want to do is we want to design a few subcircuits that will allow us to make this calculation. And so the first calculation is the open circuit voltage calculation. And if we actually wanted to measure this physically on a circuit, we would have to go and recreate open circuit conditions. So that would mean that we take the nodes A and B, we make sure somehow that there's no current coming from our probes, of course, when we're measuring A and B. And under those circumstances, the voltage that we measure would be VOC. If we're trying to find the short circuit current, then again, we take these nodes here. And the interesting thing here now is to consider that I'm going to add a short circuit like this. And since I was coming out here in this direction, we draw externally the short circuit current coming downwards. So when you're drawing your short circuit current, it's important to make sure that the directions of the open circuit voltage and short circuit current are related. So the short circuit current will always be coming out of the positive side of VOC. So if the positive end is upwards, then the arrow for ISC will be pointing downwards, not the reverse direction. There were quite a few cases where students unfortunately drew things in the reverse direction. So why do these subcircuits help us? Well, let's consider what happens when we have the equivalent of the Thevenin replaced in here. If I force the current coming out to be 0, then I'm going to have no voltage drop across the Thevenin resistance, and whatever my Thevenin voltage is here is going to be equal to VOC. If you look at the case of the short circuit connection, again, let's draw like our representative Thevenin inside here. Again, think about what happens. Now I can do Kirchhoff's voltage law across this loop, and I'd find V Thevenin minus R Thevenin times ISC is equal to 0. And this gives us the requirement that we make sure that our R Thevenin is equal to the open circuit voltage divided by the short circuit current. As long as this is being held true, then the short circuit current calculation I make will be correct. The last kind of measurement that we usually need to make when we're dealing with equivalent circuits is the idea of the test voltage. And the idea there simply is, again, let's take our Thevenin circuit and let's add the test voltage. So again, here you have to make sure that it's connected like this, VT, and IT is coming out of the positive end in this case. You'll see why that needs to be the case shortly. And remember what we do. We're only interested in the component that's driven by VT. So using the similar logic to what we had with superposition, if I only want to calculate the contribution from one source, I need to close all of the other sources, all of the other independent sources, not dependent sources. So I'm going to turn this off. If I set V equals to 0 here, this is going to turn into a short circuit. And now think about what happens when I do Kirchhoff's laws. This is going to be VT minus R Thevenin times IT is equal to 0. And then you can find R Thevenin by just taking the ratio of your voltage source voltage divided by IT. This is why we have IT pointed in the direction that we do. When IT comes out of the positive terminal, it means that we have a positive relationship between the ratio of the voltage and the current when we're trying to calculate the Thevenin resistance from the test volt method. Let's now go through and apply these on this equivalent, on a simple circuit example. Well, maybe not simple, but on a example. So the problem that we had in the exam was the circuit that you now see on your screen. And the key thing here is to try to understand what circuit we actually need to calculate the Thevenin equivalent for. And in this case, we have a circuit, we have a resistor RL here, which is our load circuit. And the Thevenin that we need to calculate is everything except the load. And so this first part really only asks you to draw the circuit in its identical form, but by recognizing that you need to find the Thevenin without the load. One of the more common errors that students can make in problems is to especially if this resistance, if a value is given for it, it's a common error to kind of leave that in when in fact you're interested in the Thevenin of everything else. Okay, so whether or not you leave a resistor in the circuit or not entirely depends on what role that resistor plays. If it's part of the circuit, you keep it in, but if it's a load, then you must take it out. And in this particular example, that resistor is a load, so we must take it out. Okay, and so this was the circuit that I expected you to draw for the answer to part A, okay, which is just RL removed and everything else kept the same. So now how do we find the open circuit voltage? Again, remember, this is removed and we have no current coming across, so that means we have no current coming in here. One of the common mistakes that was made was to, because there's no current now coming through B, to actually remove this dependent source. But remember, even though the dependent source is not drawing any current, depending on what the value of Vx is, there is still a voltage drop between this point here, which if you please, we can label as ground. There's a voltage drop between the ground and B that is equivalent to 0.5 Vx. That voltage drop is important because it affects our value of VOC. There were some cases where students mistakenly thought that the voltage from A all the way to ground was VOC. That's not the case. VOC is always the voltage drop across A and B, which are the terminals across which we're trying to find the open circuit voltage. So this is the circuit that we needed to solve for the case of finding the open circuit voltage. Okay, so there's a number of different ways that you could have gone about doing this. one way of kind of dealing with it is to just kind of cycle through and ask yourself, how many equations does it take to solve? And so if you look at this circuit, we have only one other node here. Let's call this node C. And one of them is ground. B here is not really playing a role in the node voltage method. So we essentially have two node voltages that we need to solve for. In fact, actually, since this RL has been removed, A has now turned into just a point between these two branches. So really, the only node voltage we need to find here is C. And so I think with node voltage method, this can be solved with just one equation at node C. If we tried using mesh current method, then you would have one kind of mesh current that kind of goes around this left mesh like so. And then you would have another mesh current that comes here. Because of the sharing of the common 3 milliamp supply, you would have only one super mesh equation to write, which was around the entire outer perimeter of the circuit. But once you find the mesh current, you still have to find VOC, which is a voltage. And so you're going to have to end up writing a KVL to be able to solve it. So you could have gone both ways, but I ended up solving this by using node voltage method. So we can go ahead and do that. Let's write what the node voltage equation would be for node C. It's going to be VC minus 12 divided by 9K plus VC divided by 2K minus 3 milliamps. And you could solve this equation for VC. If you did, you should find that you get 78 divided by 11 volts. And then once you find VC, the key thing is that we have to find what VB and VA are so that we can take the difference to find VOC. In this case, VB is actually equal to 0.5 Vx, and Vx is just VC in this case. So we can find that VB is 39 divided by 11 volts. And we can find VA by doing, if you want another node voltage method at node A. So, or you can just do KVL. I'm just going to do a node voltage equation at A with just two currents coming in. So I'm going to write this as VA divided by, VA minus 6 kilo ohms divided by 12. I did this all backwards. Yeah. VA minus 12 divided by 6 kilo ohms, of course. And then plus VA minus VC divided by 3 kilo ohms is equal to 0. And of course, we already know what VC is, so we can solve for VA and then subtract that from VB. And without getting into the arithmetic, you should find that VOC equals 57 divided by 11 volts when you step through the process. Okay. So the next step is to find the short circuit current. Again, we do not have our L here in the equation, but when we're trying to find the short circuit current, we're now adding our own short circuit between A and B. And in these conditions, the short circuit current is going from A to B. Why? Because the positive end of the VOC was at A. And so the arrow must start at the positive end and end at the negative end to be able to get the directions aligned correctly. And again, this is now the circuit that we have to solve. And again, you can go about doing this with any method that you see fit. In this case, I think I again used a node voltage method. One thing that you can do if you think it simplifies things for you is you can apply a source transformation on the right side of the circuit. And so if you wanted, you could, let's keep this 12 volt supply the same and draw everything. So this is going to be our dependent source around here. This is our short circuit current, which is what we're trying to find. We have our 3K resistor here. Now remember, what am I transforming between? I'm transforming between this node here, let's call this X, and this node here, let's call it Y. So this point here is node X, this point here is node Y. And it's going to be a series connection. So I'm going to have 2K in series with a 6 volt source, because you take 2K times 3 milliamps. And again, the upward side of the arrow corresponds to the positive end of the voltage, and so you can convert this way. Now, the only thing you have to be careful of, though, is what is Vx? Vx is not the voltage across the 2K ohm resistor in this position, because remember, you have to think of voltages in terms of their nodes. Nodes are the only things that get preserved when you do a source transformation or a lot of these other combinations. And so Vx is actually the voltage across from X to Y. So this is going to be our voltage value, Vx. Okay, so now let's go through and see how we can kind of continue solving the problem. Now that we have it labeled in this way, again, you can reduce this to like a one node voltage problem. So let's call this VA. And you can write what your node voltage equations are and then go through and solve for it. And then do a KCL to find what the short circuit current is. Okay, I want to come and now spend some more time on the test voltage method. With the test voltage method, again, we don't have this RL, which is between there, but we have to add our own source. And so please remember to actually draw the symbol of the source. And this is going to get connected between here. And we're going to have some current IT coming out of the positive end of the source here. We now have to turn off the sources. So when I turn off a current source, the current is set to 0. This means this turns into an open circuit. There's no current here. And this now turns into a short circuit, and this turns into a wire. And when that turns into a wire, you then go through, and now you're free to use whatever circuit analysis techniques you would like to be able to go through and find what your test volt method would give. So the key thing to remember here, though, is that you're trying to find the ratio of VT divided by IT to find your Thevenin resistance. And as long as you do that, then there's no problem. I kind of show the algebra for doing that in detail, but I did this by using dividers in part. And so what I'd like to do kind of in video is just highlight for you where the divider is. Because one of the key things is, of course, finding this voltage Vx. The Vx comes into play over here. And so let's look now. I need to have 2 series resistors. Where are my 2 series resistors? Well, I have a 2K ohm resistor here. That starts from the node right here. That now is going to be in series with the resistor here that goes all the way up until A. So I have 2K, which is in series with the 3K resistor. So where are the ends of my nodes? One of my nodes is going to be node A, and the other is going to be down here, which I'm going to designate as a ground. So what is the voltage that then goes between ground and node A? I have half volt Vx as my dependent source here, plus Vt. So I can write Vx using dividers as 2K divided by 2K plus 3K times the total voltage which spans the series combination, which in this case is going to be VA, or if I substitute, it will be Vt plus 0.5 Vx. Okay, and once you've done that, then you can just apply a KCL or node voltage method and use this expression to Vx to kind of algebraically reduce the problem. And if you go through and do the math correctly with the algebra, you should find that our Thevenin now equals 24 divided by 11 K ohms. And it's always helpful to go back and double check your answers to make sure that the resistance you found from your test volt method also is equivalent to the ratio of your open circuit voltage and short circuit current, so that you can, make sure that everything is consistent. Now, in the last part of the problem, it asks you to actually write what your Thevenin and Norton equivalent circuits are. So that would just be your Thevenin voltage in series with your Thevenin resistance and your short circuit current, which is now in parallel with your Thevenin resistance. And again, it's across the same nodes. Now, if you want to find the maximum power transfer, what do we do? Over class and lecture, we showed that we could calculate what the power that was being dissipated by a load that was attached onto here. So if I kind of go through and attach my load resistor now, this gives me my complete original circuit. Note that RL is not part of the Thevenin. So in your answer to the Thevenin circuit, you should have not drawn RL in there, and you probably did end up losing points if you did so. But for maximum power transfer, we do need to add the load back in. And if you calculate the power being dissipated by the resistor, you can find that you will get the maximum power when the Thevenin resistance is equal to RL. Again, what Thevenin resistance? It's the Thevenin resistance of whatever is connected to RL. And that is what we found in the previous parts of the problem, which was 24 divided by 11 k ohm. And then if you go substitute for this value of RL equal R Thevenin, you can find that the actual power dissipated is V Thevenin squared divided by 4 times R Thevenin. And if you crunch through the math, I got 11.2 watts as the actual power that was being dissipated. So one kind of final note about Thevenin equivalent circuits is that we don't necessarily in every specific case need to go through and find the Thevenin circuit by explicitly finding the open circuit voltage and the short circuit current. Sometimes we can just apply source transformations and reduce a more complicated circuit into a form of a Thevenin circuit. So if we can reduce a circuit so that it only involves a voltage source in series with a resistor, then we've effectively found the Thevenin equivalent circuit. And so this extra credit problem was asking you to do that for part E. And there were a number of different ways that you could have kind of approached doing it. The easiest solution, which is what I was kind of hoping students would do, would be to just kind of realize that you could combine all of these resistors into one resistor. And then if you did that, this would be 8 amps. And I think when you combined it, it became 60 parallel 60, which would give you 30 ohms here. And this would turn into a Norton circuit. And then the Thevenin circuit would be just now 60 times 8, which is 240 volts. And now you're in series with 30. The problem is that in this problem, I didn't specify to you across which nodes you needed to find a Thevenin. And what you needed to realize, though, was that the Thevenin that I've just drawn here on the slide is not the Thevenin between A and B, because A and B slice between the 10 and the 50 ohms. So the moment I combine all these resistors together and generate 30 ohms, I've lost both nodes A and B. So A and B here is not in the question, but what nodes then does this correspond to, what I'm pulling out over here? Well, I'm combining these all into one resistor. So that means I'm looking at the equivalent resistance from here to here. Let's call this node X and this Y. So really what I'm finding the equivalent Thevenin for is the Thevenin equivalent across nodes X, Y, as I've now labeled them on this circuit, okay? And so the key thing that I wanted you to realize was simply that the nodes that you were drawing out from the Thevenin and doing it this way by just doing combination and then source transformation are not the same as AB, okay? In order to find AB, since you can't actually source transform if you're trying to do it from A and B because nothing actually combines. And so either you would have to formally do, open circuit voltage, short circuit current calculation to be able to find that, or you would have to try to do some other calculations. You couldn't do it with just source transformation alone. Okay, so this was the only Thevenin equivalent circuit that you could find with source transformation alone, but it's not across A and B. Okay, so this kind of finishes the slides that I had prepared going over the exam. If you have any further questions about the test, please let me know and get in contact with me, and I'll try to do my best to reply to you in writing, posting on a discussion board or an announcement or email. I can also upload videos that are in response to questions, but I'll try to disseminate answers to pervasive questions to the entire class so that everyone can benefit from them. Take care, and I'll see y'all later. Bye-bye.